So if you remember 4-3 and 4-4, we're on log, I'll just say log functions. And a graphs. Last time we did some solving with log equations based on rewriting the log and the exponential. And then we said we have this log on our calculator, which means log base 10, right? And ln on our calculator means log base e, right? That work? So log base 10, log base e, those things are on our calculator. And we did some calculations with those. We did some solving equations with those from our calculator. All right. One thing I want to mention is some interesting concepts with this. So we've dealt with this on our calculator. I want you to just notice that if you take log on your calculator of 10 to a power, let's say we take it to the power 5.8. If I type that in on my calculator, what I should get is 5.8. Now, that should make sense based on what we saw earlier. Based on what we saw last time, anytime I have log base b of m equals y, that means m is equal to b to the y power. So what we're saying is 10 to the 5.8 is 10 to the 5.8 power, right? Which is exactly what. And the same thing with natural log. If we take natural log of e to a power, let's say negative 3.5, based on what we saw earlier, the connection, when I say earlier, I mean last class period, the connection between those two tells me that it just pulls off the exponents. So notice in some way, a log applied to a base with an exponent, as long as they have the same base, kind of cancel each other out, and you just end up with the exponent. Natural log of e to this exponent, these two sort of cancel each other out, and you get just the exponent. Now, here's another thing. What if we took 10 to the log of 31.6? And what if you took e to the natural log of 8.75? Again, just type these in your calculator. and see what happens. You should end up with 31.6 up there and 8.75 down there. Right? So notice that once again, whether I apply the log to something with an exponent or I take something to the exponent and the exponent is log of something, it's sort of undoing each other. So in some ways, the log, not in some ways, in a lot of ways, the log is the inverse function of the exponential. All right? Now, think about what that means for the graph. And so let's get right into the graph. Oops, that I should have. Most everyone was not. There it is. So let's think about what that means for the graph of the logarithms. So let's do our base function. F of x equals log base b of x, all right? And we'll let b be 2 for right now. Okay, we'll go base 2. Does that make sense? The graph of the log function looks like this. Now, it might be hard to see, but if, actually, let's do B again. If I would have drawn or graphed the exponential, notice that the exponential function and the log function are symmetric about the line y equals x. All right. That's an indicator that those two are inverse functions of each other. Remember that? Back when we talked about function inverses. So it's basically drawn in the same way that all of our every point, let's say we have 2.32, 4.993. There's going to be another point, 4.993. I won't even graph that. 2.32. I can't scroll it. But you guys see where I'm going with that. It doesn't jump as well. Doesn't jump as well over there. But you guys get the point, hopefully. So every point with an xy, x comma y point in the exponential function has a y comma x point corresponding in the log function. By the way, remember that the exponential function had asymptote at x equals 0. Or I'm sorry, not x equals 0, y equals 0. And the log function is going to have an asymptote at x equals 0. So this log function has a vertical asymptote whereas the exponential function had a horizontal asymptote, right? That also means that the domain of my log function is limited. I can't plug in 0 or anything negative, right? And that should also make sense in terms of what the log function means, right? If I were to plug in a negative number here, I'm saying a negative number is a base to a power. Well, remember, we assumed all of our bases were greater than 0, not equal to 1. So if all of our bases are greater than 0, anything positive raised to a power is still going to be positive. So we can't have any negatives, and we can't have 0 here, because if my base is above 0, this is a non-zero number equaling 0. So I can't plug anything 0 or anything negative into my log function. That's the domain. And so, like I said, our base log function is log base b of x equals f of x. Doesn't matter if you say f or g or whatever. So that's my base log function. And this is continuous passes through one, 0, just like our exponential pass through 0, 1, base exponential pass through 0, 1. This passes through 1, 0. There are no sharp corners. We have a vertical asymptote. At x equals 0. And then the domain is everything bigger than 1. They say bigger than 1, so you did bigger than 0. All numbers that are bigger than 0. All right. That's our base exponential function. Keep doing that. Now I used base of 2 on this. Let me cancel out this. So I used a base of 2, but if you use a base that is smaller than 1, notice the flip around the x-axis, right? So if your base is smaller than 1, we flip around the x-axis. So the two options for the look of the graph is that if my base is bigger than 1, we're gonna have a asymptote of x equals 0, but the graph is gonna go down to negative infinity there. If base is smaller than 1, then my asymptote is going up to positive infinity on the left. All right, so those are kind of the two options for the look of the graph. I will say the more common one is probably with base bigger than 1. I'll just write these off to the side. This is base smaller than 1. Obviously, when I say smaller than 1, we want bigger than 0. And then basically all we do is we take that base logarithm and we shift it in appropriate ways to figure out what we want. So in other words, let's take our base log function and shift and stretch from there. How am I gonna shift and stretch my base log functions? All right, let's just say translate. Translate. So if I have, let's say y equals log base b of x, and then I plus k at the end, what do you think that does? Well, to vertically shift, we add k after we've done, right? So this is a vertical shift. Horizontal shift. By h means that the shift happens on the inside of the function. If I multiply by a on the outside, that's a vertical stretch or contraction, depending on if a is bigger than 1 or smaller than 1. But it's a vertical stretch. Or shrink. And then if you want to do a horizontal stretch or shrink, you put that on the inside. So if we have a function, or we have Yeah, let's say function. That is something like 3 log base 2 of x plus 1 minus 7. Something like that. Okay? This graph is translated from the base log function by, well, it's going to be a vertical stretch of minus, or did I say stretch? Excuse me, I misspoke. A vertical shift down 7. A horizontal shift got a +1 in here, and it's supposed to be x minus h. What's that mean for the horizontal shift? You just going left, correct? Does that make sense? Left 1. Right? And it's actually vertically stretched by a factor of 3. All right. By the way, if we shifted our log function from the base log function, that also shifts the domain. But really the only thing that applies to the domain shift is what's inside the log. Does that make sense? So we shifted this function left and down 7. The down 7 doesn't affect our domain. The vertical stretch doesn't affect our domain. The only thing that affects our domain is what's inside this argument. So the domain here is all x bigger than 1. I'm sorry, I said bigger than 1, bigger than -1. Domain. Let's talk about the domain. So the domain, the inside of the log function, needs to be greater than 0. Is that right? So if you're trying to figure out the domain of a log function, just say, well, the inside piece of the log function has to be greater than 0. And if I solve that means my domain is all x that's greater than -1. Does that make sense? And by the way, that means the vertical asymptote also on this It's simply x equals -1. It's when the inside argument of the domain is equal to 0. You better understand the connection between vertical asymptote and the domain. The same number, right? Be very careful though. Domain is all numbers bigger than whatever number, or I guess it could be less than if the argument was 1 minus x or something like that. But vertical asymptote has the equal to sign, right? X equal to a number. Does that make sense? Let's do the same thing for another graph. We'll do vertical shift, horizontal shift. Talk about the domain, talk about the asymptote. Take f of x equals, I'll just do log base 5 of 2x minus 10 plus Great. We get 2x minus 10 plus 3. 2x minus 10 inside the log base 5 plus 3. By the way, if this were log base 3, would it make any difference? Well, not the shifting part. Obviously, it would make a difference on what the graph looked like, how steeply it rose, but as far as the shifts go, it doesn't matter, right? Shifts are the shifts. So this is a vertical shift. This would be up 3 plus 3. Now here's one that people sometimes get wrong because there's a coefficient out in front of the x here. What's the horizontal shift? And it might be easier at the same time to talk about the domain. The domain means the inside argument has to be greater than 0. We add 10 and divide by 2. Let's go ahead and do that. And we get x greater than 5. Which also means that the vertical asymptote is x equals 5. What's this mean about my horizontal shift? This means my horizontal shift is horizontal shift of 5, right? We got the asymptotes there. Shift, and it's to the right because it's a positive 5. There's also a horizontal stretch of the 2. That's what the 2 comes in. Actually shrink. So the domain is all numbers bigger than 5. Vertical asymptote happens when x equals 5. All right. Let's think about what other things we could deal with our log functions. Well, one of the other things that we can deal with our log functions is the x and y intercepts. Let's take and find x and y intercepts of f of x equals, I forgot what the I'll just do that. I won't put any vertical stretch on it this time. Is that okay? How do I find the x-intercepts? How do I find the y-intercepts? Done this before, right? Find the y-intercept. Let's do that first. Plug in 0 for x. Now you might say, oh, this is tricky. This is not that tricky. All right. When we plug in 0, log base 2 of 1 is 0. I used it. Everybody understand why log of anything of 1 with any base is 0? What you're saying is that log of any base of 1 equals 0. It's saying that 1 is equal to anything to the 0 power. Right? And that's a true statement as long as my base is greater than 0, not equal to 1. Okay, follow that? So the statement that log base b of 1 is always 0, no matter what the b is a restatement of the fact that anything to the 0 power is 1. Okay? So log of 1 with any base is 0. So that means my y-intercept is 0, -7. Let's find the x-intercept by plugging in y equals 0 to this. So we go log base 2 of x plus 1 minus 7 equals 0. add 7 to both sides. And then this is something we solved last class period, right? Something like what we solved last class period. So we can say, well, that means the argument, the x plus 1, has to be 2 to the 7th power. That's just a rewrite. So x plus 1 has to be 128, subtracting 1 from both sides. You get x equals 127. So that means the x-intercept is 127, comma, 0. Is that all right? I did that. Again, this was the same tool from here. This was the same tools I was using last class period. Okay. Let's do the same for this function. We've done all of our shifts. We've looked at our domain. So let's find the x and y intercepts of this. I want you to go try to do this on your own. In this case. All right, so if we're trying to find the y-intercept, I'm going to plug in 0 for the x value. Now, if I plug in 0 for the x value, what I end up getting is a log base 5 of -10 plus 3. Now, here's what we should know about logs. Remember, the domain of logs is numbers greater than 0. If you plug in something that is a negative into a log, it is not going to exist. So this does not exist. I'm just going to put DNE for does not exist. Okay? And so in this case, there is no y-intercept. Which we probably already knew if we referenced back to what we knew, to what we were talking about earlier. Remember, we dealt with this exact same function earlier, and we said it had a vertical asymptote at x equals 5. And if we're understanding enough to know that, well, here's my x equals 5, and I know the function does this, it never can go back and cross the y-axis, right? So if my function is over here, not going to have a y-intercept. And that happens with a lot of logs, right? Shift this way. And then I didn't do the negative thing, but if you put a negative in front of the log, we flip over the x-axis, but if you put a negative on the inside, then it flips to this, right? Flips over. But you could technically have a log that looks like this if I threw a negative on the inside here. Does that make sense? But the point is, doesn't cross the y-axis. And not all log functions do, as we see here. Now, as far as the x-intercept, it will cross the x-intercept, it will cross the x-axis at some point. Plug in 0 for y. And then we're going to solve this for x. The nice thing is I can solve this one for x using the tools from last class period. This means that the argument inside, 2x minus 10, should equal 5 to the negative third power. Add 10 to both sides. 2x is equal to, goodness, that's going to be an ugly, let's just take 10 plus 5 to the negative third. Is that okay? It'll be easier to write that way instead of a fraction or an ugly decimal. And then divide by 2. And I'll just write the final answer because I haven't wrote this on my calculator yet. So let me write the final answer. 10 plus, by the way, 5 to the negative third is 1 over 125. So that's why I wanted to avoid that fraction. 10 plus 5 to the negative third divided by 2. I get 5.004 in decimal form. If I wanted to round it to 2 decimal places, that's 5.00. I'll keep it at 3 for right now, okay? So the x-intercept, 5.04, comma 0. I'm just keeping it at 3 right now, not because that's what you'll have to do on Moodle, but rather because I want you to notice it's just not 5 even, that's all. Us to know that it's not 5. Any questions about finding the y-intercept or the x-intercept? Now, in both of these examples, it kind of worked out nicely that my log base 5 of -10, we knew did not exist. And my log base 2 of 1, we knew had to be 0 because of the interplay between log and exponentials. But if while solving and trying to find a y-intercept, I end up with, let's say, log base 4 of 19. That's going to be harder to calculate, isn't it? I don't know what power of 4 to what power is equal to 19, right? And so the question is, how am I going to end up figuring out what these things are? And more in general, how do I solve equations when I'm trying to solve for logs if they're more complex than the ones I gave? All right. What if equations involve multiple logs of the same base? What if equations, so on and so forth? So in order to figure out things like these, we're going to have to know some properties of logarithms. And that's what 4-5 is all about. All right. So 4-5 is properties of logarithms. And let's just state this up front. Since log base b of m equals y really means m is equal to b to the y power. We're going to have some unusual looking properties. A lot of us so far have dealt with functions that have had properties that are almost akin to distributive properties. And so we've seen the distributive properties so much that we almost want it to work for every function. Well, it turns out it does not work for logarithms. Okay, logarithms have weird properties. Let me give you an example. So let's talk about some properties of logs. And I'll also try my best to indicate what exponential property this is connected to. All right. So let's look at some properties. I'll just say logs, but of any base. So here's an interesting one. If I take log base b of m, and then I add it to log base b of n, I end up with log base b of M times N. So when you add on the outside, you get multiplication on the inside. That's a weird property. Let me just try to, at least in this case, talk about the corresponding exponential property. The corresponding exponential property is that if you take b to the y power times b to the x power to whatever, you have to add the exponents. What this is an exponent, log base b of n. That's like the x or the y in this. And so this is like the other one. This is like the y or the x. Let's just say this one's the x, this one's the y. Okay, it's saying that if I'm looking for the sum of the two exponents, then that's like taking b to the x times b to the y and saying what exponent on b is this. So the corresponding property is that. Similarly, if I do a subtraction of two exponents, I get that. I have to divide on the inside. And that's the similar thing, b of x divided by b of y is equal to b of x minus y. Okay, so those are a couple of properties of logs that work weirdly. We've kind of seen this, but this is, we're going to do two exponential properties. If I do log base b of b to any power, I should get that power back. Now that one's obvious, we've done that one before, right? By the way, what's this mean when p is 0? When p is 0, what do we get? When p is 1, what do we get? So this property earlier we were talking about with p is 0, obviously. But it can be more generalized there. And we mentioned this when we dealt with the calculator, log base 10 of 10 to some weird power is that weird power. Log base e or the natural log. of e to some weird power is just that weird power. No matter what it is. These are two that we'll use a little bit of. I'm gonna erase this part of it because I'm gonna write one of them. Log base b. This is the interesting thing. Here we have base b to a power. What if we had some other base to a power? It turns out you get p times log base b of n. In other words, the exponent came out and multiplied the times what's in front times log base b of n. Now this is a crazy rule. Crazy looking rule. But it actually just is a corresponding exponential property. And the corresponding exponential property is saying this: log b to the x raised to the p power is b to the x times p, or p times x. I'll just put p times x, is that okay? What's the x in here? The x in here is log base b of n, that's the exponent x. So it's saying p times x, this exponent, has to be equal to log base b of, get back b to the raised to the p power. That's what it's getting at, right? So if you raise, this is like a b to the x raised to the p power. So n here is like a b to the x. You get this. So that's what an exponent land we call power to the power rule, right? Power to power rule. So this is just the log version of a power to power rule. And you can kind of trace it through. I'm not going to trace everything through. That takes time and we don't need to spend time doing that. But all of these are fairly straightforward to trace through. Every time b to the x is your m, and b to the y will be your n. And each one of these, b to the x is your m, b to the y is your n in each one of these. So these are four properties of log, and it doesn't matter what base. So it could be log base 2, log base 10, the natural log base 1/5. This works for any base we want it to. Okay. So let's use some of these properties. And we can use them in both ways. So by that, we could simplify into a single log expression. Let's do this. Let's say we have log base 3 of 4x plus 1 plus log base 3 of 6. So if I want to simplify that into a single log expression, I can look and say when we add logs with the same base, I can combine those two by setting this equal to log base 3. And then in the inside, I take the product of 4x plus 1 and 6. So 4x plus 1 times 6 on the inside. So if I was to combine those into a single log expression, it'd be log base 3 of 24x plus 6. And a lot of times those single log expressions are easier to use than the more complex versions when you're solving equations. Is that all right? Let's do another. Simplifying a single log expression. Let's take log base 4 of 8x squared plus log base 4 of 3x well, this would be log, actually, I want you to do that. And then if you have time, let's do this, log base 2 of 4x to the third minus log base 2 of 6x that way. Right? And then if we have time, yeah, might as well keep doing it. 4 log base 8 of 3. Then 3 log base 5 of 2x squared. All right, so I have 3 problems on the board. No, 4 problems, 4 undone problems. Try to do each of those. All right, let's go ahead and do these. Hopefully, it doesn't take you too long to do these. Again, I've erased the log properties that we're gonna use, but I'll reference them. So the first one is, we have the same base, and we're adding two logs with the same base. That means I can take that log base 4 and then multiply what's inside the first one times what's inside the second one. And I get log base 4 of 24x to the third. By the way the Moodle does it is it'll say, here's this thing, it's equal to log of this, what is this? And so you have to fill in what this thing is. So you have to fill in the 24x to the third. Okay. On the next one, well, this is subtraction of logs with the same base. So anytime we subtract, we take, in this case, this first argument, divide by the second one. It is very important that the minus sign, the one we're subtracting, is the one that goes in the denominator, okay? So be careful about that. The one you're subtracting goes into the denominator. And you can simplify this if you want. Log base 2, this would be 2/3 x squared. 4/6 is 2/3. X to the third over x is x squared. Now these first few, I did all with arguments that aren't just numbers. You could have obviously had thrown in just numbers in there as well. And your calculations become a little bit easier with just numbers. This one, we did just that. We just threw in a number, 3. So we take log base 8 of 3 to the 4th power. That's log base 8 of 81 as a single log expression. By the way, what is log base 8 of 81? Heck if I know, right? This is something we still have to address with another log property. Okay, I just want you to realize that. That's all I'm saying. And there's another log property out there that we're going to have to utilize to figure out what is this number. 8 to what power is 81? Bigger than 2, less than 3, right? Because 8 squared is 64, but 8 to the 3rd is much bigger than 81. So we'll figure it out somewhere between 2 and 3. And we'll catch that. All right, so that's just things to come. On this one, we take 2x squared and we have to raise that argument to the 3rd power. So we have log base 5 of 8 x to the 6th. Remember how to raise power to powers again. X squared to the 3rd is x to the 6th. 2 to the 3rd is 2 times 2 times 2 or 8. So be careful about that. But other than that, that's using our properties to get into a single log expression. Right? So we took our properties into a single log expression, simplified. That's one way of using those properties. Another way of using those properties is calculating a more complex expression. If we know let's say we know log base b of m is equal to, may I have any favorite numbers? What do you use? Doesn't matter. We'll use 2.1, I guess. And log base b of n is 0.7 or just 0.7. I'll write 0.7 so you can see that. So let's say I know those two things. I don't even know what M and B and N are, but I know those two things. So here's what we're going to calculate. Let's take log base B of M times N and figure out what that has to be. Well, based on my properties, I can't calculate it directly from this look. But if I say, well, that's log base B of M plus log base B of n. And I know what this one is individually, and I know what this one is individually. This one is 2.1, that other one's 0.7. So actually, the product of m and n inside the argument log b, that all comes out to just a 2.8. So that's another way we can use it. We can start with log of a messy looking thing inside and break that down. And then if I know these numbers, I can get an answer for log of a messy looking thing inside. I want you to try this on your own. Take log base b of m over n. Try to figure out what that is. Then take log base b of m to the third power. And here's a tricky one. Take log base b of m to the fourth power divided by n to the fifth power. Try those three. Is get all these. Let's do these. So the first one is the reverse of our log base b's subtract formula. So we have log base b of m divided by n is equal to log base b of m minus log base b of n. Again, remember, denominator is the one you're subtracting. So subtracting log base b of n in this case. And we know log base B of n is 2.1. Log base B of n is 0.7. So when you divide log base B, n divided by n, you get out a 1.4. Now the next one is log base B of m to the third. We're going to take out the 3 and we're going to put it in front because that's the power rule of logarithms. Right? That I can take an exponent of an argument and multiply that exponent times the log of the argument without the exponent. Now we have log base B of m. We know that is 2.1. So this is simply 3 multiplied times 2.1, which is 6.3. All right. On this one, well, this one we're going to have to combine kind of both properties here that we use. We have m to the third divided by n to the third inside of log base B. So what I would do first is say that has to be, since we're dividing, log base B of m to the fourth minus log base B of n to the fifth. Then on each one of those, I can apply the power rule of logarithms. Log base B of something to a power, I can take that power and multiply it out front times the log. And I just get log base B of whatever that something is. So I'm going to get 4 log base B of m minus 5 log base B of n. Now log base B of m, I know what number that is. That's 2.1. So that is 4 times 2.1 minus 5 times 0.7. And when all that is said and done, I end up getting 4.9. By the way, this rule where we can take an exponent out front, that's going to be one of the central rules in solving exponential equations that we're going to use over and over and over again. I'll write that down at the end, but that's going to be big, very, very big. Taking that power out front. Because it allows us to take a variable. If we end up with a variable here, allows us to take that variable. Now we're multiplying. Instead of taking a variable in the exponent, we're multiplying by that variable. Any questions about any of these rules that we've been dealing with? So those are the kind of 2 questions that people use with these rules. All right, directly. Now, The last rule of log is called the change of base rule. And it says this: if you want to take log base b of m, and b and m are not nice numbers that match up, then what we can do is we can take a nicer base. I don't care what it is. Let's call it A instead of B. I think the book calls it N, but we'll call it A. It doesn't matter. We can take a nicer base. Let's say base A. And it turns out log base B of M is the same thing as log base A of M divided by log base A of B. All right? And that's for any A that's a legitimate base, so greater than 0, A not equal to 1. Okay? It also, B has to be greater than 0, B not equal to 1. Okay. So again, all of our bases always have to be bigger than 0, not equal to 1 for things to work out. We always assume that. So as long as our bases are bigger than 0, not equal to 1, this rule works out. Now that's pretty crazy, right? Let's go back to one we did last time. We said something like log base 2 of 32. Remember how we calculated that? We said, what is 32? 32 is 2 to the 5th, so that must be a 5, right? That's what we did last time. This time we could have said log base 2 of 32 is equal to log base 2. 32 is 2 to the 5th. So what does our rule say? Those 2's cancel out, we get a 5, right? 5. Okay. What this rule says is it says if you took log base 2 of 32, if you took, for instance, the log on our calculator of 32 divided by the log on our calculator 2, and I plunge this into my calculator, I should get a 5. Or if I took the natural log of 32 on my calculator divided by the natural log of 2 on my calculator, I should also get a 5. That's pretty strange, isn't it? Let's see. What we mean by that. So here's my calculator, as always. That was the last problem I did. But, so let's take log of 32 divided by log of 2 on my calculator. Change of base rule says this should be fine, should be the same thing, right? Natural log of 32 divided by natural log of 2 should also be 5. It's pretty crazy when you think about it, because natural log of 32 is not a nice, pretty number. And natural log of 2 is not a nice, pretty number. All right. So it's saying some irrational number divided by some other irrational number happens to be 5. That's pretty interesting, huh? But this allows us to do the things that we were talking about. Like we said, I don't know what log base 8 of 81 is. But if I wanted to calculate log base 8 of 81, all I have to do is take natural log of 81 divided by natural log of 8. That's log base 8 of 81. Roughly 2.11. Okay. And so anything, any log base, anything of any other number can be calculated. Let me rewrite that. So log base 8 of 81, that's something we had on the board earlier, is the same thing as natural log of 81 divided by natural log of 8, which is roughly 2.11. And if I said, let's calculate the following things, log base 5 of 892. Let's say log base 6 of 0.02. Go ahead and calculate those and see what you end up with. Using the change of base rule, obviously. All right, so I use natural log, but you could use log base 10 as well. So when I typed it on my calculator, I use natural log. But if you use log base 10 on your calculator, that's fine too. You're gonna get the exact same answer. And that's answer on this first one is about 4.22. Okay, rounded to a couple of decimal places. On the second one, again, I use log, natural log. Be careful, by the way, on this one. Change of base rule. The base is always in the argument in the denominator, and the argument here is always in the argument in the. Careful about that. 0.02. We have on the top, inside of the natural log, 6 inside the bottom. and you end up with about negative 2.18. By the way, you can kind of check these if you want. Obviously, these are rounded numbers, but if you take 5 to the power of 4.22, you should get pretty close to 892. You won't get exact because it's rounded. But if you took 5 to the 4.22, I got 890.54-ish. And that's, again, because that's rounded. If I went out further, more decimal places, and then put it in, I get closer to 892. Same thing here. If I do 6 to the power of negative 2.18, I get roughly 0.0201, blah, 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 blah. So close, not exact because of the rounding. So everybody know how to use the change of base rule? Now this looks sort of magical, but it's not really. If we want to ask where did the rule come from? Or how could we end up with the change of base rule? It's actually just a few of the rules that we've dealt with already. All right. So let's let y, whatever y is, be log base b of m. All right. So also, in other words, if we wrote this as an exponent, b to the y is equal to m, or m equals b to the y power. Now here's the key. Now let's examine some other things. Let's examine log base a of m. That has to be equal if I replace the m with a b to the y, which I can do, right? Because b to the y was equal to m, just replace the m with a b to the y. And then based on my exponent rule, or my power rule of logs, I can take that y out front. Now I'll rewrite this in a second, but this is essentially my change of base rule right now. So what I have is y times log base a of b, that thing here, is equal to log base a of m. I'm going to divide both sides by log base a of b. And then remember that my y originally was log base b of f. So it's basically just rule manipulation for my log rules in a clever way to get a change of base. Okay with that? So it's just log rule manipulation. So that's where the change of base come from. It's not some magical formula. It's just those rules I was dealing with earlier. Rule manipulate, rewrite, those types of things. Any questions about this so far? The log properties. Now, I mentioned this earlier, but we're going to start solving equations that are either exponential and log equations. The most important rules on solving the exponential and the log equations are going to be that power rule of logarithms. That power gets brought out front when solving exponential equations. We often use those rules. And again, just so that we're on the same page, the rules that often we use, that rule, I apply log base b to b to the power, you get a power. If I apply log base b to m to some power, the power comes out front, multiplies log base b of m. And then on occasion, that change of base rule, log base b of m equals log m. A is so those rules are ones that we use often in solving exponential equations. Now, these aren't the only things we ever use, so be very clear. These are not the only things we ever use, but they're very common to use when solving exponential equations. Okay. Does this work? Make sense? All right. Well, then let's move on to the next section. And the next section is, in fact, solving exponential equations. This is what 4-6 is. 4-6 we might solve some log equations too. In sort of the reverse way that we solve exponential. All right. And anytime we're solving exponential equations, there's different techniques. Let's use our first technique. Okay. Our first technique is going to be solving an exponential equation when I have the same base. This one we've actually already seen before. I didn't call it this before, but we've seen this before. If I have 5 to the x plus 2 power is equal to 5 to the 9th power. What do you think I can do? Well, if I have the same base, I can simply just set the exponents equal to each other. When we have same base, we can set exponents equal. So we just get x plus 2 is equal to 9. When I subtract 2 from both sides, I end up with a 7 for my x. I think we did that earlier, and that wasn't last time, but a couple of class periods ago. Did something to that. Now, obviously, if we do not have same bases, then we either have to manipulate until we get to the same bases, or we have to use a different technique. All right. So let's take and solve this one. 2 to the 3x plus 8 is equal to 32. Now, I chose this because we've dealt with 32 before, right? And we know that 32 can be rewritten as 2 to the 5th power. And if we can rewrite 32 as 2 to the 5th power, now we have 2 to a power equals 2 to a power, and we can set those exponents equal to each other. So we get 3x plus 8 is equal to 5. Solving, subtract 8 from both sides. 3x equals -1. Or 3x equals -3, so you get x equals -1. Don't forget that when you're doing things and you have, let's say, let's do this, 9 to the x power equals 1 over, let's do 27 to the x plus 4 power. Nine and 27. 27 is not a power 9, 9 is not a power 27, but they're both powers of 3, right? So I can rewrite 9 as 3 squared and raise that all to the x power. Now, how do I want to do this? Let me do this first. I'll do 2 steps here. (27), 1 over 27 to a power is 27 to the negative of that power. That'd be negative x minus 4. Is that okay? Okay, still with me there? Negative x minus 4. And then 27 is 3 to the 3rd power. Now, when I apply my exponent power to a power rule, I get 3 to the 2x power is equal to 3 to the negative 3x minus 12 power. And then now I have the same base. I'm going to add 3x to both sides. And then divide by 5. And I get an x value that is negative 2.4. Okay, so sometimes it does take a little bit of algebraic manipulation to get to this, like same base, to get things with the same basis. So that's solving when you have the same base. I'll manipulate. Some of them are easier than others, but manipulate until you have the same base. And then if you have a base to a power equals the same base to a power, I can set those 2 powers equal. All right. So that's the first technique. Now that is not probably the predominant technique that we're going to use in this section and also in the next section. The next section is just solving exponential equations with word problems, right? So the predominant technique, which I'll call the second technique, basically is isolate the exponential function and then apply logs to both sides. Or I should say, isolate the exponential expression and apply logs. Let me give you an example of that. So basically, the second technique is what I'm going to say is just using logs to solve. All right. So solve using logs. Lots of different ways to do these. Let's start out with a more straightforward one. Let's take e to the x plus 17 is equal to 892. So we want to solve this. So the first thing we do is we isolate the exponential expression. We have e to the x on this side plus 17 equals this number. We're going to subtract 17 from both sides. Then we're going to get e to the x is equal to 875. Now, you can think of this in a lot of different ways. I think of this as applying natural logs to both sides. What I'm going to do is I'm going to apply natural log. You could also think of it as rewriting it into a log expression. The trouble with thinking of it as rewriting into a log expression is that oftentimes if our base isn't a base that's on our calculator, it's not quite as nice. So let me just say it this way. So I think of this as applying a natural log to both sides. If I take a natural log, apply it to the left-hand side, and a natural log applied to the right-hand side. What happens on the left-hand side is that this goes away, this natural log and the e cancel each other out, and I'm just left with the x. You know what rule this is? This is, I'm using the rule that says log base b of b to a power is equal to just that power. Okay, I'm using that rule to be able to say if I apply natural log of e to an x, I just get the x on the left. And on the right, I have natural log of 875. And I can simply just type in natural log 875 into my calculator. Or the exact answer is natural log 875. The rounded answer would be 6.77. That's rounded to 2 decimal places. Okay. Again, you can go from here to here using an exponential rewrite into a log equation. Or I like to think of it as just applying natural log to both sides. that okay? In both cases, you're going from here to here. Either rewrite into a log expression, or I think of it as applying natural log on both sides and using this rule. Does that work? So we isolate, we get the exponential expression on it by itself, alone, and then we sum. Let's do a couple others. Let's say I took 10 to the 2x minus 4 plus 8 is equal to 2,117. All right, the first thing I'm gonna do is isolate. I'm gonna subtract 8 from both sides. That isolates my exponential piece. I get 10 to the 2x minus 4 is equal to 2109. Now, I'm going to apply log base 10 because I'm using base 10 here. So I'm going to apply log base 10 to both the left and the right-hand side. And I end up getting 2x minus 4. I should probably put that in green instead of the other one side green. Is equal to log base 10 of 2109. Now we still have to solve for x, but we can solve for x by just adding 4 to both sides. And then dividing by 2. By the way, be very careful. We are not adding 4 to the inside of the log function. We're adding 4 outside of the log function, right? Of the log expression 20. So make sure you add and divide correctly. Your numerator is going to give you some number, some ugly irrational number, I assume. And then when you divide that by 2, I ended up with about 3.66. Again, be careful how you type it on your calculator. I calculated the entire numerator and then I divided by 2. So, again, be careful of how you deal with that. Let's do another one. Let's take this. Let's solve 1500 e to the 0.09x is equal to let's just say 27,000. Is that right? So this time I need to isolate the exponential piece. Now, in this case, I have a coefficient in front of the exponential piece. But that's not a big deal. I just divide by 1,500 on both sides. Okay. So I still need to isolate the exponential piece even from its own coefficient. So divide by 1,500 before I get it. When I take 27,000 and I divide it by 1,500, I get 18. So E to the 0.09x equals 18. Now I apply natural log to both sides. I'm using natural log because it's E, base E. And by the way, once you've done this enough, I wanted to do at least the first few times, right? Every step down, but once you've done it enough, you'll say apply natural log, and on the left, you'll just say, oh yeah, that's gonna be 0.09x. And on the right, it's gonna be natural log 18. So eventually you'll probably stop writing this step here. And just say, well, if I apply natural log, this is what I get. Once I have that, now all I have to do is divide both sides by 0.09. If I round that answer to a couple of decimal places, I got 32.115 or 32.12. Wait, let's get 32.12 on the calculation scale. Now you can see where this is going to come up in application problems. You're going to say, well, with continuously compounded interest at a rate of 9%, if you invest $1,500, how long is it going to take to reach $27,000? Remember, that was this piece on the left is essentially PE to the RT, right? And so that's the type of thing that's going to come about. We'll look more of these next time. I think we'll stop here, but we'll solve more exponential equations next time. And so far, you'll notice that on the second technique, my base has always been E or 10. Right? E or 10. And so next time we'll say, what if we don't have base E? What if we don't have base 10? And it turns out the process is exactly the same, just this left-hand side works a little bit differently. All right. Any questions about this? Okay. All right. So next time we'll finish this up. You have the vast majority of tools that you need for the entire test. But we will finish this up next time, okay? All right, I'll see you Wednesday.